So what if you could find the maximum of every single moving window in a massive stream of data? Not by rescanning it over and over, but in one single super efficient pass. Well, today we're going to tackle a classic interview problem that has just an absolutely beautiful O of n solution. Let's dive in.
Here's the core challenge, right? You've got an array and this little window of, say, 3 elements. As that window slides across the array, one step at a time, you have to report the biggest number inside it. Now, you could do this the simple way, but it's slow. There is a much smarter approach.
So here's our game plan. We'll start by defining the problem. Then we're going to use a really simple analogy to build our intuition. After that, we'll walk through a real example, prove why it's so incredibly fast, and finally, we'll look at why any of this actually matters in the real world.
All right, first things first. Let's get on the same page and really break down what the sliding window problem is all about.
So the goal is pretty straightforward. We need to create a new array, and each element in that new array is going to be the maximum from a corresponding slice of the original. Simple enough to say, but making it efficient, well, that's where the magic is.
And this right here, this is the whole point. The naive way where you rescan all k elements for each position, that's O of n times k. If your array is huge, that's a disaster. Our goal is O of n, linear time, which means no matter how big that window k gets, the total time only really depends on the size of the array n. That is a massive difference.
So how in the world do we get from O of n quality rings all the way down to O of n? Well, the key is a clever data structure, and the absolute best way to understand it is with a fun little analogy, the bouncer's line.
I love this because it takes something abstract, a data structure called a double-ended queue or a DEQ, and turns it into something we can all picture. So imagine this. The DQ is the line to get into a club, and the people trying to get in, those are the indices of the numbers in our array.
And this line has 4 simple rules. 1. New people, or indices, always join at the back. 2. If a new person is stronger, meaning the number they represent is bigger, they kick out anyone weaker who is in front of them in the line. Why? Because those weaker people can now never be the maximum. 3. If the person at the very front has been waiting too long, their index is now outside our window, their ticket expires and they have to leave. And 4, the most important rule, the person at the very front of the line is always the champ. They're the index of the current maximum value.
Okay, now that we know the rules of the club, let's see our DQ in action. We're going to walk through an example, step by step.
All right, let's say our array is 1, 3, -1, etc., and our window size is 3. At step 0, the number 1 comes along. Its index 0 gets into the empty line. Easy. Then at step 1, the number 3 arrives. It's bigger than 1, so it kicks index 0 out and takes its place at the front. At step 2, -1 arrives. It's smaller than 3, so it's no threat. It just lines up behind it. Now our first window is full. Who's at the front of the line? Index 1, which points to the number 3. So our first result is 3.
Now the window slides. At step 3, -3 comes in and just joins the back. The max is still 3. But now, watch this. At step 4, the number 5 arrives, and this is a huge moment. 5 is bigger than everyone currently in line, so it kicks out index 3, then index 2, then index 1. It clears the entire line. Then index 4, for our value 5, gets in, and the max for this window is, you guessed it, 5. And this dance just keeps going. The number 3 lines up behind 5, then 6 arrives, kicks out both 5 and 3, and becomes the new champ. The max is 6. And finally, 7 arrives, kicks out 6, and becomes our final maximum. You see how the DQ is always just dynamically keeping track of the best candidates? The winner is always right at the front. And there it is, the final result, the complete array of maximums for every single window, all calculated in just one pass. It perfectly matches what we just walked through. So we know it works. It feels fast. But let's prove it. Why is this solution actually linear time? What's the secret sauce?
The entire proof, believe it or not, boils down to this one simple idea. Think about it. Over the entire run of the algorithm, each index from our array gets pushed onto the DQ exactly one time, and it gets popped off at most one time.
This leads us to something called amortized analysis. It sounds fancy, but the idea is simple. Even though one step might do a bunch of work, like when our number 5 cleared out the whole line, the total work is spread out very evenly. Since each of our n elements results in at most 2 superfast operations, a push and a pop, the total time is directly proportional to n. It's O(n).
It's that simple.
And when you put it side by side with other methods, it's just no contest. The naive scan is way too slow. Using something like a max heap is better, sure, at ON log K, but it's still not the best. Our DQ method, at a clean ON, is the undisputed champion for this problem.
So, okay, this is a great solution to a classic interview problem. But is it just a brain teaser? Where is this actually useful? Let's talk about the real world and what you absolutely need to remember for an interview.
The truth is, this pattern is everywhere. It's used for things like calculating moving averages in real-time data streams, for building filters in signal processing, for spotting weird behavior in monitoring systems, and even in finance for keeping an eye on risk over recent trading periods.
All right, if you're in an interview, you've got to nail these 4 points. 1. The invariant. The DQ always stores indices that point to values in decreasing order. 2. The proof. It's amortized O of n because every element is only touched, at most, twice. 3. The detail. You have to store indices, not the values, so you can check if they've expired from the window. And 4. The pitfall. Don't forget to check the front of the line first and pop any old indices that are out of bounds.
At the end of the day, this idea of a monotonic queue for finding mins or maxes in a window is a really fundamental pattern in computer science. So the question I want to leave you with is, now that you get how it works, what other problems could you go out and solve with this amazing technique? Thanks for tuning in.